In this video, we're going to talk about stationary points. I'm using a new computer and I haven't had a lot of time to plan this, so I do apologise in advance. I will do the best I can. So firstly, what are stationary points? Stationary points are points on our functions where the tangent to that function would have a horizontal slope. So I'll use the textbook to assist with this explanation. The first example we'll look at here is the local maximum. So if we look at this blue function here, looks a bit like a quadratic, you'll see that along the blue function there's one spot and one spot only where if we drew a tangent it would be a horizontal tangent, it would have a slope of 0. And that is the point here. And we would call this one a local maximum. And we call it a local maximum because before the point the function is increasing, so all the tangents to the function before the local maximum point have positive slopes. Once we cross over that x value and go the other side, the tangent will have a negative slope alongside any point on that function. So the first type of stationary point we have is called a local maximum. A local minimum is very similar, but the other way around. So in this case, any point before the stationary point on the function would have a tangent with a negative slope. We get to the local minimum point itself and we have a tangent with a horizontal slope, a 0 slope. And then after that point, we would have tangents with a positive slope. So that indicates a local minimum. And the next example we have is called a stationary inflection point. And we can see in these examples that the function, in this case, the function, any point along this function is increasing. Any tangent to this function would be positive, so the function is increasing up until the stationary point. But rather than turning around like it would in a maximum, it actually goes the other direction here. So in this case, the function is increasing all the way to the stationary point. And after the stationary point, the function is still increasing after the point as well. It turns around and has that particular type of shape. Over here, another example of a stationary inflection, but in this case, the function's decreasing, has a tangent of 0 at the stationary inflection point, and after that, the function is still decreasing. So if we think about a point on this curve here, it also would have a tangent of a negative slope. Stationary inflection points, the most common one you've probably already seen in a function that is probably quite well known to us is y equals x cubed. So if we have a quick look at that, there's y equals x cubed. We've seen that one before, and you can see it has that stationary inflection point where the function is increasing. There's a horizontal tangent here at the origin. Then we flip back the other way, and the function continues to be increasing as we continue further along in that direction. So that is a quick rundown of what a stationary point is. The next thing we need to do is to be able to calculate where these stationary points are and what values they might have. That's the main thing we need to do here. We can use our calculators, particularly for the maximums and minimums. We can enter the function into our calculators, press a button, and it tells us those values. But we need, as part of our course, to be able to calculate these stationary points using calculus, using the derivative. But by all means, use a calculator to check and confirm your answers. You have that tool at your disposal. It's a very wise thing to do. So let's just do a couple of examples to get us started. Apologies, when I did the initial recording of these examples, I had the microphone not turned on. So I'll have to do a voiceover to explain what I was doing with these examples. So what we have here is we have the function 2x minus 3 to the power of 3 plus 4. The first step we will need to do is to find the derivative of that, and as you can see here, we're doing that using the chain rule. So we've got 3 times 2x minus 3 squared times by 2 for 2x minus 3 all to the power of 2. Okay, so there's the derivative. So to calculate the stationary point, we need to work out the first thing we need to do is work out where the derivative is equal to 0. In this case, we would apply the null factor law, and it would be when the bit in the brackets there, the 2x minus 3 is equal to 0, is when that function is equal to 0. So if we just do a quick linear equation to work out what that would be, which I think is going to come up any second. So when 2x minus 3 equals 0, and we solve that, which would be quite elementary for a Year 12 student, we'd end up with x equals 3 over 2. So the stationary point occurs in the original function at the x value 3 on 2. The derivative is equal to 0 at the stationary value, at the x value of 3 over 2. Now the next thing we need to do is we need to do a sign diagram to determine what type of stationary point it is. So we know there's a stationary point at 3 over 2, but we haven't ascertained at this point whether it's a maximum, a minimum, or a stationary inflection point. So we must do a sign diagram. And even if the question doesn't specify to do it, please make sure you do a sign diagram as part of your working out. It is expected, even if it's obvious, if the graph is drawn there and you can see what type of point it is. So here we go, we're doing our sign diagram. There's our stationary point at 3 on 2 when the derivative is equal to 0. And in this instance, you can see, regardless of whether we use a value as our test value below 3 on 2 or higher than 3 on 2, it will be in the brackets, which ultimately gets squared afterwards. So regardless of what x is, whether x is a negative number or x is a positive number, it will be squared afterwards, therefore resulting in 6 times a positive number. So for values less than 3 on 2, our corresponding y values would be positive, and also for values greater than 3 on 2, they would also be positive. So our sign diagram would be plus plus. So in this case, we have an example of a stationary inflection point. So I believe we're about to go through how the sign diagrams help us determine what type of stationary point we have. So when we have a sign that doesn't change over the stationary point, that indicates an inflection point. So plus plus or minus minus would be an inflection point. This one here, we have plus then minus. So if our sign diagram indicates plus then minus, that would be the indication of a local maximum, because the function is increasing up until the stationary point, then it's decreasing after it. So that would be a local maximum. Plus minus indicates local maximum. Minus plus, our function is decreasing until it hits the stationary point, then it starts increasing. In this instance, we have an indication of a local minimum. And if we have plus plus or then minus minus, that indicates a stationary inflection point. Okay. I believe the next thing we now need to do is, okay, we know that the stationary point occurs at 3 over 2. What is the corresponding f of x value, y value for 3 on 2 of the original function? We know that it put it into the derivative will get 0, but we need to know where it is on the original function, so we need to substitute that 3 over 2 into our original function at the top there. And for that sort of routine, somewhat tedious sort of calculation, that's what we want to use our calculator for. We don't want to be spending a lot of time doing those sorts of calculations. We want to do it as quickly as possible. So we'll likely just use the calculator to do that, which I think I'll do any second now. Yep. So what we're doing here is we're just calculating what the original function would be if we substitute x for 3 on 2 to work out the corresponding y value, which from memory was 4. Okay, so that I think I cut that a little bit early, but that's okay. That was just using the calculator to calculate the corresponding y value, which was indeed 4. So what we're doing now is, as I've suggested in previous lessons, as we go through these questions, I highly recommend that you graph the function and the derivative. You have a much better understanding if you visualize the graphs as well as doing the calculus and the algebra. So in this case, there's the original function there. We can see that it has a stationary point here at x 3/2 and y 4, which is where the cursor is sort of hitting at the moment. And that clearly indicates the stationary inflection point there, where it's increasing. And now we're graphing the derivative. And the derivative, as you can see, will be equal to 0 at the stationary point. So it touches the x-axis right there at 3 on 2. But as you can see, because as our sign diagram showed us, it was a positive value on either side of that value. So that's why we can see that our derivative function comes down, touches the x-axis, and then immediately goes back the other way and remains positive. So we've got the positive. And that is it. Thank you very much.